Welcome everyone for this webinar regarding the breakthrough metrology advances of 3D optical profiler. I'm Samuel Lesko. I'm the Director of Application Development for Stylus Optical Profilers and Tribology. In case you need to contact me further on, you have my email address, samuellesko at bruker.com. Feel free to drop further technical discussions regarding this webinars or the technologies. So quickly, Bruker is a wide company, so I represent here the nanosurfaces divisions, which aim to study surfaces through optical, stylus, tribologies, nano-annotations, and high-resolution fluorescence microscopy. So today, the aim of the webinar is to focus on 3D optical profilers, and we'll get a state-of-the-art review on what this technology can provide. As such, some of you may know YCOS. So YCOS was first of all merged to Vico Instruments to form the Metrology group, and the Metrology group of Vico Instrument has been then purchased and plugged into the Bruker organizations on end of 2009. Since then, the YCO has still continued on evolving, generating new innovations, as you can see across the years. Today, we will focus on white light interferometry technologies with the Contour series, but also it is very important to understand that we are expanding toward new technologies as well with focus variations. So a second webinar will be hosted in the coming weeks discussing about the added values of focus variation with the Contour Lesko, especially regarding very rough samples. Today, what you will learn is all about white light interferometry. So it's clear that white light interferometry in the past years has dramatically evolved and has moved forward to many different fields. So what you will learn about is how the boundaries for vertical and lateral resolution has been pushed, as well as how white light interferometry can nowadays scope with very rough samples and be able to measure actually steady slope. Upon to this, we see as well evolutions toward characterization of thin transparent films, which were before an issues and which now become fully characterized by white light interferometry techniques. So I will shortly touch upon this and bring you the solution which has been implemented by us. But also, as what you will learn in terms of users is how the software has been advanced. Simply because the optical profilers are becoming a real facility system with multi-user, it is very much important to have a capability through the software to extend the productivity of the system, notably with flexible multi-analysis or reporting capabilities, as well as to start and combine information such as not only topography but also infinite focus images, or last but not the least, having a flexible automation such as you can run multiple experiments overnight, for instance. As said, whenever you have questions, please drop your questions into the chatter. We'll answer them at the end. So first of all, I will start digging into how the interface can play a role into the user experience. So what some of you may be used to is the former interface with Vision 32. So we moved since 2010 to Vision 64. As it is named, Vision 64 is a full 64-bit software, and it brings to the user extra power regarding post-processing capabilities, but also handling large files and large quantity of data sets. So what you see is the interface has been fully revamped, such as you have a precise panel where you have the results, where you can control analysis, and whenever you toggle back to the measurement setup, you will be able to toggle to brand new interface where you only see the videos and the measurements parameters to make it simpler and easier to set up. And then whenever you have the measurement is done and over, you will get back the result. Also, this new software interface brings extra flexibilities and advancement regarding data processing. For that, you have some kind of examples of what we call the analysis tree. So usually, and it's more and more common, that for given measurements, you may want to extract multiple informations. And here this is fully possible through this tree of analysis, where you see that one single data set is post-processed with like a median filters, with cylinder removal or fourth order polynomial removal. But then you see as clearly two separate analyses. And this is from the same data set. So the first one screened down high pass filters, such as you will get more the roughnesses and detect the defect such as peaks or valleys, and that's the reason why you have such a multiple region analysis that automatically segment the surface into peaks or valleys in order to get statistic there. And then you have all the roughness analysis, which is actually based on low pass Gaussian regression filter in order to access waviness. And then you can, with the new ISO norm 2578, you can get access to the S parameters, which allow you to plot SA, for instance, for the mean waviness, or to get the SAL, which is the autocorrelation length, telling you how much a certain step is repeated into the surface. So all that is now done in a single data set and all the way through the tree. And of course, the user can call up offline this tree and change parameters or change the tree, and later on store everything into a database and repost-process in a batch hundreds of data sets, for instance. So the idea is saving time and get all the results you need in a one single go. Furthermore, Bruker has released in a few years from now the Vision 64 map. So Vision map is an OEM software from Digital Surf. So some of you may use an external mounting software. So what we wanted is to bring this extra power into directly Vision 64. So Vision map brings to you advanced 2D contour analysis, like automatic analysis of that 3D screws, and you define angles, radius of curvature, spacing of the thread, and report that into a CSV file directly there. The point is, we have integrated in such a way that user can simply record with Vision 64 data, and then automatically in the background the software will save the corresponding MMNT file from Vision map and store all the information. So what you see in that region, for instance, is the Windows Explorer that shows that you automatically save the OPDX file, which is the Vision 64 format from Bruker, and then the MMNT, which is from the Vision map, which help you to get access to the extra features. And in that case, you will generate automatically a nice report, which we were missing. So generating a report, storing advanced analysis or results is now straightforward with the addition of a Vision map. Well, so this was all about software capabilities to make the whole user experience easier, getting higher throughput. But now it's about advances regarding the white light interferometry modes. And indeed, there were several progresses. So the first of all is when we think about white light interferometry, there is an element of sensitivity toward light saturations. But sometimes, in some occasion, especially for some kind of rough samples, like the wire-bound surfaces, you may want and get lights, because if you don't bring light, you may miss data sets in some regions, and you have a dropout of data in other regions. Nowadays, this vertical scanning interferometry mode, or called VSI mode, is very much insensitive to saturation. So user can just really saturate a lot, such as even the darkest regions get measured. So basically, there is an improvement regarding the data set you can collect, and this is also one of the point of the reason why we are able now to measure rough surfaces, is simply because we have ability to saturate, get higher light, and get back signals. Also, from the standard phase shifting interferometry and vertical scanning interferometry, we have added the so-called VXI. So VXI slots in between phase shifting and vertical scanning, and in that respect, we will have ability to automatically measure different samples while having the best out from the performances. So with this VXI mode, the system automatically selects between 3 different algorithms. One algorithm called high fidelity here will help to study very smooth silicon carbide mirrors. So it's more or less a PSI-like mode, but instead of shifting fringes by 1/8 of the wavelength, the system actually vertically scans and uses the phase signals in order to rebuild the 3D topography. So it's very important is whenever you have surfaces with high differences that goes beyond the coherence length of filter light, or beyond the depth of field from high magnification objective, we can leverage out the issues by just vertically scanning, but still aiming to get the 0.1 nanometer vertical resolutions through this modes. The second application addressed by this mode is really about MEMS, or a sudden jump of clean surfaces. So whenever you have few micron step, but you like to get really sub-nanometer vertical resolution both on the top and the bottom surfaces to study, for instance, how clean the etching process was, you will just go for VXI. And what you see here is definitively you don't see any spurious bat wings we were used to see with vertical scanning interferometry. So the VXI mode corrects this very well. Last but not the least, you can still use the VXI with high speed, and the system will automatically select high speed whenever you start and measure like a random sample such as a coin. So the coin will be measured nicely, even with VXI, simply because the system will recognize a certain spatial frequencies and amplitude of spatial frequencies, such as it will automatically toggle for a VSI type of algorithm. So that being said, this means that a user who is very not familiar with white line interferometry will simply use VXI, and the system will automatically select for him the best results with the best performances. So it's a very tremendous advantage and progress to make the system fully capable for multi-user, for instance. As I said, VXI also brings data integrity. So what you see is the same features, same objectives measured with VXI on the left, with VSI on the right. So you see like background noise of vertical scanning, which is around few nanometers. So you see some kind of noise appearing on the bottom or top of the part, while VXI shows a perfect sub-nanometer vertical resolution, and you see actually a defect or detail on top and the bottom of this MEMS structures. So same one, as I said, the bat wings or the bad wings, depending on how you spell it, you have some kind of spurious effect on the sharp edges there, which is fully corrected whenever you use VXI system automatically without any further interaction. So in terms of data integrity, accuracy, this VXI mode, which is present by default on a new platform, will definitely bring a good progress and advantages. Also, usually when you start to use let's say a mode where you cleverly combine amplitude and phase signals, it might be challenging to make it very universal. As I've shown already, we were measuring silicon carbide, we were measuring MEMS, we were measuring a standard coin. And likewise, VXI is absolutely robust and very universal. Here is an example of let's say crystalline patterns on the surface used with the Android 15X objective. So you see 20 by 27 microns only, so pretty high resolutions, very close to the diffraction limit, on a very steady, smooth surfaces organized in random ways. So you could really imagine a better surface to probe robustness. And what we see is we draw a line here on that pyramid. We nicely see the slope around almost 40 degrees, and the system still operate well in a fully automated way. So in short, this new modes bring ease of use, is capable to scope multi-user usage, because basically user does not require any understanding somehow or pre-selection from user of the mode. The system will do the selections by itself. As I was saying as well, VXI mode brings also higher amount of accuracy, especially for sub-microns roughness. It is well known that verticals scanning on the bottom right, let's say, tends to enhance and artificially scale up the mean roughness. And this is what we can see by measuring a stainless steel shaft made for precision manufacturing with an SA mean roughness around 0.3 microns. If we do that with VXI, definitely the roughness is more aligned with what is expected, around 0.2 microns. Furthermore, this is a shaft, so on a border basically from that left side or right side, or that left side and right side, what you can expect is a slope where fringes are closer and closer. And what we see is VXI brings less noise and is more homogeneous signals to noise ratio across the surface, from location where fringes are very well spaced up to location where fringes are compressed. And what you can see is indeed just visually you can start and see some differences from VSI modes from the center and from the side. So there is an element of robustness, accuracy, fidelity about data that makes a VXI mode very practical. So now, after this new mode, and we'll see later on that there are also more new modes coming, I will explain about the gain of 4 lateral resolutions. There is like a debate in community of how far the optical profilers can go, and definitively there are elements here you will see that will show that we are coming actually very close from atomic force microscopies. The reason for that is we have designed through Olympus a specific OEM objective of 115x objective. This objective works in air and has high NA values around 0.8, but also, and this is very important for the user, with a decent working distance. So the working distance is almost 1 millimeter, which makes operation safe. We are not with objective around 0.1 or 0.2 millimeters, so basically 100 microns from the surface. So you can still study rough surfaces with that objective without, let's say, crushing the objective in there. So this 115x objectives allow us to gain a bit of lateral resolutions. But what about really the limits? For that, we need to work about the mode itself. So in VXI mode or PSI mode, we obtain a mode which allows us sub-nanometer vertical resolutions. And by using super resolution algorithms, we can gain actually lateral resolutions through that. And what you see over there is an example of gain. So same location, same 115x objectives, and we look for gratings with a spacing around 300 or 250 nanometers. So the scale in Z as well is the same. So what we see by doing a session in normal mode is some kind of definitively pixelized and at the limit of what the system can resolve, and actually the depth is not right, so it's around 20 nanometers, which is absolutely wrong. If we do it with the Acuity mode, which consists to do 10 measurements on the same location, the system computes all the data to figure out exactly where every point is, and it does subsampling between pixels. So this image there has twice more pixel in X, twice more pixel in Y, and what you can see is that depth is now the right one expected by the customer, and also you can clearly see that the details here of the defect is absolutely dramatically different. So you understand that this grading is a stamp, is made of polymer and stamped. So basically on that image you understand that the wall polymer resin which was heated has partially collapsed and got some kind of adhesive behavior by capillary forces, rather than like thinking that this is a defect. So you really see the advantage of gaining lateral resolution is, first of all, we can measure the grading correctly, the depth is right, the periodicity is right, but also we can have a clarity on exact reason for the defects. So this mode works very well for smooth surfaces because we need to use a VXI mode with high fidelity or standard level, so any mode with sub-nanometer vertical resolutions. And for instance, we have used it to very different surfaces. So it can be like chromium on glass with 200 nanometer space lines. It can be on silicon oxide. So this is optical waveguide with sub-wavelength patterns. So you have 190 nanometer sphere diameters spaced by 900 nanometers. So you clearly nicely see that. And actually, what we see here is not the real topography, is more the optical response and the phase shifting occurring while the light is reflected from silicon versus silicon oxide. And what we see as some kind of moire around is actually the subtle changes felt by the light regarding the phase shifts around. So it means the whole guide is not homogeneous. So that way you can directly characterize how homogeneous the refractive index is around that system. So pretty interesting. We already saw some 250 nanometer gratings in polymers. And final example is about thin SU8 photoresist resin. So what we see is a nice series of holes around 320 nanometers size and spaced by 1 microns, which is already a great achievement. But usually with that type of surface and the thin transparent layers of SU8, now we have transparency issues for 3D optical profiling, which is understandable. But actually, by the fact that we have a higher NA and shorter depth of field with the 115x objectives, we simply avoid the transparency. So this is one of the other use of the 115x objective, is to get rid of transparency of thin film and have the accurate and fiddle measurements of the surface. So now if I go to the gain of slope, so slope will be split into two areas. So we can think about slope which are absolutely smooth. So this is what you will find out with on the micro lenses or on etched patterns like the PSS pattern on the sapphire for LEDs or polysilicon substrate. In that case, we have steady, smooth slopes. So what you can see is, in that case, there is no other way than to use a high numerical aperture objective. And the 115x objective with 0.8 nicely allows the measurements on the glass micro lenses or sapphire patterns or polysilicon substrate. So this expands the capability of the system, such as you can now measure the surfaces. And usually, again, VXI mode will play a significant role to help you getting the best out of the structures. However, smooth, steady slope are very specific, very niche applications. The common slopes met, for instance, in precision engineering are all rough. So there are an element of roughness, and this roughness actually greatly helps stand objective from wide line interferometry to collect data. And this has been a dramatic changes since the release of the contour profilers, is this ability to capture this roughness by injecting more light with two LEDs, but secondly being able to saturate and getting the data back. So here what you see as the first example on the top left is abrasive cones used for tumbling and removing burrs from precision engineering parts. And what you see is a nice stitch data across the slope, and at the end here you get a slope around 65 degree. And the slope can be measured simply because those abrasive parts are rough. And you measure this with intentionally a 5x objective, so low magnification. So we go beyond the numerical aperture and we collect data in a nice way. We can do the same with some kind of long working distance Linux objective, which are also new. So having 34 millimeter working distances really helps to measure like the hypoid pinion gears, and be able with the slope capability to measure part where there was a sliding and material removal and depositions while doing the tribology test. So this is definitely something interesting that open up white light interferometry toward rough surfaces, such as saw blade, for instance. So you see on the left a brand new saw blade, and a saw blade after a certain number of cycle of cuttings. So you can nicely look and see how the slopes differs and how much roughness you gain along the slope. So all that is definitely working with white light interferometry. So the technique itself has dramatically evolved and now expanded toward rough surfaces. The same way as with the blade surfaces with a 50x objective, we have a tiny amount of roughness, so meaning tiny means around 0.1 microns or 0.05 microns assay along the slope, which is enough for the 50x to capture that the 54 degree slope, which is far beyond the normal numerical aperture limitation of 50x objective, which is around 25 degrees. Or here with 5x, we are more in a range of 5 degrees and go up to 65. So the conclusion is actually the rougher the slope is, the better it is nowadays for white light interferometry. So that's something we need to change perceptions on about the technologies, and certainly I encourage you to give a test or propose or send to us some part if you think that white light interferometry could be able to measure them, or on contrary to challenge us and see whether we can get this measurement done. And now, as I said, there is a new field which corresponds to collapsing two pieces of information. So we are looking through an optical objectives. Even so, it's interferometric. Objective sees light, sees intensity or reflected light. So there is an element where we can collect optical view together with topography. And this is what we made through what we call Elite. So Elite has had external lighting with some kind of angle, such as we can light up, let's say, slope, but also get the light through the diffusive reflections. And why the system measures, we have a clever algorithm that captures not only topography, but also capture intensity or color at the point of focus. So at the end, what you obtain is all in focus intensity or color map, which is collected by the same objective, same location, same time as the topography. And as you can see here on this intensity or color image, there is absolutely no more presence of fringes or whatever. So we have a clean intensity color image, which can then be correlated together with topography. So you see here on this printed paper, we nicely see in topography fibers. We can draw a line, and this line is drawn the same way on a color image and get all this together. Or you can decide to overlap the color image on top of the 3D topography image, such as you get the direct visual correlations. So the The main idea of this elite option as well is to render interferometric objective more like a stereo microscope. So it is important to know that not only you collect intensity and topography together, you get an element of ease of use. So this is an example of trying to focus on like ceramic PCB board, and this board, as you can see, without the ring illuminators around, is poorly contrasted. This is what we expect with interferometric objectives. And it starts to be very challenging to find out where the focus is, trying to find and pick the moire from the fringes. Instead, if you light up the ring illuminator with the side illuminations, you light up the colors, you light up the edges and details, so it starts to be much easier to focus and go then launch the measurements. And for the measurement, for instance, you can still switch off the ring illuminators and measure with only the coaxial light, such as you have better data sets. But that being said, focusing on porous ceramics, on white type of plastic, focusing on the black rubber, or on the PCBs, start to be extremely simple and as easy as using a regular optical microscope. So it's I really encourage you to consider that, because on the day-to-day life, one of the first bottleneck for any optical profilers is how quickly you can focus on surface before to launch measurement. And now with white light interferometry, it becomes as easy as using a bright field objective, more or less. So here's the examples. So we can nicely measure a stamp and get a 3D image with the color overlap. So you see that on top. You see the top view with just topography. Also, the interesting thing is white light interferometry nicely pick the top surface, especially whenever you have a transparent protective layer. So here you have thin, let's say, polymer filmed on top of metal embossed parts, and this protective film is nicely spun out in a non-ambiguous way through white light interferometry, so you exactly understand where the surface is and topography as well. But of course, having the optical view helps you to find out how the metal has been embossed, understand why here you have a depression simply because the polymers has partially covered, and just follow the big steps. So in that case, you can even know whenever you have disruption of that protective film on that location. So here you see the depressions, which is simply due to that part. So everything starts to be obvious, very conclusive, driven process, and so it's really had extra information that leads to extra information toward that. Also, whenever you have colors, the software has been also fine-tuned to take advantage of that. So nowadays, for instance, to select the gold pads here, the gold connecting pads over a substrate, what you see within a topography image is start to be very spurious and challenging to really properly segment, especially up to the end. Why here on the software you can segment through the color. So basically you will select the area, you add the colors, you move this type of cursor for the tolerance, and then the system will automatically select the area where you have this features, and then you can mask and get the topography exhibit. So now you can define the relative height between the different pads, you can define the height versus a substrate, you can determine the volume which was used for of gold. So basically everything starts to be very straightforward to spot out and identify patterns through the colors. And now I will finish with a discussion about, again, a new mode that extend measurements toward transparent thin films. So what has been made is we use light as now reflectometers. So basically we look for the merit functions and look for analysis of that light being forwarded back. In that case, we can define the area and location of interest, and the system will find the local minima to find out the real thickness. So this help very much about the capability to measure dielectric thin films. This film can be regular, can change or be partials. Where the system doesn't work is, of course, whenever you have a more complex functions of refractive index, such as whenever you have metals, whenever it start to be very rough, or whenever you have a mix of multiple layers. But that being said, this is what you get. So now the film algorithm not only cover large film above 2 microns, but also films up to 100 nanometer thickness. And what we obtain is simply a map of data, like here, where you see how much the thickness varies and what is the fluctuation. So you see here we have a film thickness of around 365 nanometers plus minus 3 nanometers. So basically what we did is, just to benchmark that everything was working fine, we tested silicon oxide over silicon and getting some measurements versus nominal values. And what you can see is it goes very well regarding the measurements of those values with the same settings. So the system works as let's say vertical scanning interferometry, and it brings back top surface, bottom surface, and thickness variations all together. And finally, I like to go more versus automations, because whenever you have all those details, what we have is definitively ability to do multiple samples. So our aim was to scrape automation such as it can scope with all kind of different conditions and in the same way be very simple to use. So this is an example on how you set up a wafer, so you can determine the wafer type and where the notch is or the flat is. Then you define the number of row and column and the width of every die. And within the die, you can define a certain numbers of locations you want to measure. And whenever you define this to one die, it is fully ported to to all the dies. And then you can simply graphically click and enable any cells, and the system will, for instance, automatically label them in a way it is measured. So it will start to 1 and then move to 2 and then move to 3. So you exactly know what the system does and how it percolates through the measurements. So all that is very much default automation. And to further push throughput regarding automation, especially whenever you have thousands of location to test, we have improved the tip tilt. So first of all, the tip tilt can be done with an objective which is different from the measurement objective. And secondly, the system can redo multiple tip tilt until it is set versus what you ask. So if you want and ask a null fringe, especially to measure very low roughness, like sub-nanometer roughness, you really need to ensure that the fringes are null as much as possible. the system can redo it until it reaches a certain residual over there. So you don't have to tell the system what to do. The system will simply do it. So for instance, if you move to a sample which is flat, more likely a single auto tip tilt will be good enough. But whenever objective moves to the next sample, you might need some iteration, and the system will, at the first measurement, automatically perform 3 iterations, then move on and go only 1 iteration for the next location, saving time in that way. The second one as well is you can decide as well to tell to do the auto tip tilt only to certain numbers of locations. So either all location, either every second or every 10 location, in order to save time. Likewise for autofocus. So all those features are standard defaults from automation, from the software. So as you can see, it's a very complete and make it efficient towards highly automations applications. And then basically, as I said, we use now Vision 64, which is full 64-bit. So we can do daily measurements with a large numbers of data sets. So stitching now goes 1000 images daily, full resolutions. So you can really measure this coins and then further zoom in a digital way and still see very nice lateral details. So the system can measure, like here in that case, more than 2,700 data sets on the 38mm diameter dollar coin. And this is due to the fact that we have effectively 64 bits that breaks the limits in terms of memories for those images. It's just a question of time and passion, and that's the reason why it's interesting to have automation software to automatically measure the samples overnight and have a free system during the day for other purposes. So as a conclusions, as you saw, white light interferometry is not the same than 10 years ago. It has a very much higher lateral resolutions. So if we discuss about confocal definitions, we reach a lateral resolution of 75 nanometers. So meaning we can resolve details of 150 nanometers. In the same time, we can have sub-nanometer vertical resolutions, which is like 10 times better than the standard vertical scanning interferometry over tens of micron step. Also, slope capabilities has moved up, so we can measure, like with a low magnification, we can measure 65-degree slope. So everything starts to be possible to measure even rough samples. Whenever we speak about rough samples, of course, we might need large stitching, which is now possible with 64-bit. But overall, if I really could summarize all what has been made, is a big flag about ease of use. So if you think about 10 years ago and a system now, I really encourage you to come and see the latest system, because 10 years ago all that was not present, and the overall experience as a user is absolutely different. So whenever you like to get a refresh, feel free to contact us. You may have extra informations through the website. You can also contact your local application engineers over there. Thanks for your attentions. If you want to download the new Vision 64 software, because it's free of charge for our user, feel free to do so. It does help for the post-processing of all data sets anyway. So you can use the multi-analysis tree and get, in that case, benefits for 64-bit capabilities. That being said, Thanks for your attentions, and I like to open up now the Q&A sessions regarding details. All right, so I see is like there was first of all questions regarding thin film, and the question is about what kind of additional informations do we need to know the thin film thickness. So what we know, we need to know the chemical compositions of the thin film and the substrate. We also need to measure onto a reference surface the optical response. By reference surface, I mean a surface where you don't have any thin film. So that's the two elements you need to know. The third one is getting an idea of the thickness of that film, because for any kind of reflectometry level you have multiple possible solutions, multiple local minima from the merit function, so you need to tell and bracket this such as the system can just focus and find the right solutions. There was also another questions about that time for the vertical scanning interferometry regarding the modulation threshold values when measuring very smooth and rough surfaces. So in that case, I would be it depends exactly on how much contrast you have between the high and low intensity fringes. If you tend to have a strong contrast, you can still put the modulation thresholds on the smooth surfaces around 10 or 20 in order to eliminate noise. In case of very rough surfaces with or weak contrast, you will certainly go to 1% or even a lower, like 0.2%, in order to collect data. Still with the compromise of having slightly more noise, but the idea is to put more lights and get modulation threshold lower. There was an element as well regarding another question. So for people using all NT9000 series, to see whether the 115x objective can operate. In that case, the answer is yes. You can add 115x objectives because the NT9000 series has a strong LED illuminations got through the two LEDs. For people having holder system, we have to check what kind of surfaces you want to measure with 115x objective. For in terms of can we have VXI mode, Acuity mode, and thin film on our old Vision 32? The answer is basically Vision 64 only has such a feature of VXI and Acuity and thin film. You can still use Vision 64 offline to post-process any data generated by Vision 32 and benefit for the multi-analysis tree. But unfortunately, all the codes behind to run the specific modes belongs to Vision 64, which is linked to a certain hardware from the contour. So all that is please check and contact your local sales or application person in order to have an idea on possible upgrade path for your old NT9000 or NT3300 or 1100. The other question was how long can be the integration time before image acquisition? Usually acquisition time now goes very fast. We still use the, let's say, 1x speed, 3x speed, 7x speed or so, but this speed is linked to the camera, the frame rate, and this rate has been boosted up. So basically nowadays a 1x speed is already 3 or 5 microns per second scan, which is usually 5 times faster than the old system. So usually you can expect that the standard acquisition time is 10 seconds, sometime lower for flat surfaces. For rough surfaces is more like a minute. But that's basically all what we can hear about how fast we scan. Are the data from old Vision software compatible with Vision 64 software? Absolutely. So we made it compatible in it both ways. So Vision 32 saves data set in OPD format, and OPD format is fully recognized by Vision 64. But furthermore, Vision 64 saves both OPDX, which is a new file format, but also still we can save with Vision 64, we can save OPD file format, which means that people having a database of data of 10 years collected with OPDs and they still want to measure and analysis, make performance analysis with Vision 32, they can still do that. They will just save the data and acquire data through Vision 64 and then port that to Vision 32. So there is an element where so let me okay so I can see that there are more and more questions regarding all this. So let me summarize and get everything done in that respect. So I will further on answer the questions. Please feel free to drop me an email at my address here if you have more questions. I see there was a very huge interest from you. Keep in mind that we will have soon a second webinar regarding focus variations. Please feel free to join whenever you will see invitation. So I'd like to wrap up and thank you for your attentions and have a good day or good evening. Thanks and goodbye.